Hello students, today we are going to start with electromagnetism. You must have studied about magnets. Perhaps last year we had a lesson on magnetism, and you must have studied about electricity. Current electricity was a lesson last year in 9th standard. This year we are going to study the combination between these two. We studied about the properties of magnets. Magnets, they always point towards the north-south direction when they are suspended in the air. Like poles, they repel each other. Unlike poles, they attract each other. And about current electricity, convectional current always flow from positive to negative, and the flow of electrons are from negative to positive. Then we studied about rheostat and so many things. We are going to study all of them and beyond that in this lesson. Now, there was a scientist by the name of Hans Oersted. He studied the properties of magnetism and electricity, and of course he was a professor in a college and a physicist himself. He had his own lab at home. So now, while explaining the properties of electricity, he had accidentally kept a magnetic compass where his experiment was going on. He found that whenever he used to put the switch on, the electricity on, there was a deflection in the magnet. Now the current flowing through the wire should be sizable, otherwise for less current there won't be any deflection. So that's why there was no comparison found between electricity and magnetism for a long time. Only after Hans Oersted's experiment it was found that this current electricity and magnetism, they are interrelated. That means there is a relation between both of them. Okay, now what was the experiment which Hans Oersted performed? Let's study that in detail. Okay, so for that you need a conducting wire. Okay, so this is a conducting wire. This is a battery. Okay, this is a key, and there is a rheostat over here. You know what is a rheostat? Rheostat is used to increase or decrease the resistance. That means the current can increase or decrease. Okay, and this is a key over here. This is a key. This is a battery. Now, supposing this is your east, west, north, south. Okay, and the magnetic compass is kept in the north-south direction. Now, again understand, the current over here is flowing from south to north. See, this big line means positive. So the current flows from positive to negative. And just see the wire. I mean to say the compass. The compass is in the south-north direction. Initially, when the key is open, when no current is flowing through this, the compass points in the usual direction, that is north-south direction. But when he put the switch on, and when the current was flowing through this, there is a deflection observed in this compass. The deflection in this compass was found in the west side. That means the needle deflects towards the west. Okay, and see how the wire is moving. The wire is above the compass. Okay, now deflection is increased when you increase the current. With the help of rheostat, you can increase or decrease the current. So if you increase the current, the deflection is increased. Now he observed later on that when you increase the number of turns in this wire, then also the deflection increases. In other words, the deflection in this compass is been observed to increase only when the current increases and the number of turns increases. So now here in this, the compass is below the wire and the deflection is towards the west. It is according to this rule, snow rule, south north over wire, south north over west. That means the electricity is flowing from south to north and the wire is above, and the deflection of the wire is towards the west. Now what happens if you change the polarity of this? This is positive, this is negative. You just change the polarity, that means change the battery. Bring negative over here and positive over here. In that case, the deflection of this compass will be opposite to the west. That will be towards the east. So in that case, the compass will move towards the east. Okay, before it was north south direction when the switch is off and when no current is flowing. But when the switch is on, now when the polarity of this is changed, then the compass points towards the east. Okay, so that is what is the observation he observed. Now what did he do next? He took this compass and kept it above the wire. Okay, now the wire is below and the compass is above. So and then he put the battery in this way as it was before. The current is moving from positive to negative, or in other words, the current is moving from south to north. Only the difference is this compass is kept above. So when the compass is kept above, then the deflection will be towards the east. Earlier when the compass was below, the deflection was towards the west. Now when the compass is kept above, the deflection will be towards the east. And what happens if you change the polarity of this current, or if the current moves from north to south instead of south to north? That means if this positive is made over here, put over here, and negative over here, then that time the deflection will be towards the west. So that is his experiment. So what do you conclude after seeing this experiment? We conclude that whenever electricity flows through a wire, there is a magnetic field around it. Okay, and the magnetic field increases by increasing the current or the number of turns in the wire. Now, Hans Oersted performed many experiments in his own lab at home, and he found out so many interesting facts. So we'll study about that now. Okay, now he took a cardboard and he made two holes in the cardboard, and he passed a copper wire around it, and on the other end he connected to a battery and a key as usual. Okay, and of course there is a rheostat also. So this is what he did at home. Okay, and the current is moving from positive to negative, and he put iron filings all over. Small pieces of iron we get, it's as good as sand size, and he put it over here, and he gently tapped the cardboard. He observed that the iron filings arrange themselves like this in a circular fashion. Okay, over here just see how the iron filings are arranged themselves. And so he observed that the magnetic field are like this in this order. Just see, this is in the anti-clockwise direction, this is in the clockwise direction. So he concluded that the movement of the magnetic field when the current is going from down to top is according to the right hand thumb rule. So this is the right hand thumb rule. See, if the current is moving upward, the magnetic field are going like this. See, anti-clockwise direction. Can you see? Anti-clockwise direction. So that is what he observed. Whenever electricity is flowing from down to top, and when the thumb is held like that, so imagine you are holding the conductor with your right hand. So thumb denotes the direction of the current, and the curled fingers denote the direction of the magnetic field. The direction of the magnetic field is how? It is anti-clockwise. This is anti-clockwise, and this one will be opposite. Okay, so now when he increased the current, he observed that the magnetic field increases. There will be more number of circles, and the concentration of the ions will be more at these circles. Wherever the circles are there, so at that point there are more concentration of the ion filings. And this point at the center, let's take it as K, is called as the neutral point. So at this point there is no magnetic field, because here it is clockwise and here it is anti-clockwise. They cancel each other. So magnetic field at the point K is 0. Did you get it? Now we'll go on we are going to study about the properties of this current carrying wire and having a magnetic field around it. So the experiment which we are going to perform is the solenoid experiment. Now what is a solenoid? Now solenoid is a current carrying wire which is wound around in such a way that it forms a helical loop. I'll show you the direction. You take a wire and you just wind around your finger like this. That is a helical loop. Okay, either you wind it around like that, or you take any non-conducting substance. Like for example, you take a cardboard. Now see, this is a cardboard. See, this is a cardboard like that. Okay, and you wind a large number of copper wire around it. Okay, now I'm able to draw only few number of turns, but you have to, while performing the experiment, you have to always take large number of conducting wires. Okay, there is a switch and there is a rheostat, ammeter, many things are there, but for the sake of understanding what is a solenoid, I have drawn this experiment. Now see how the current is moving, like that it goes around that. So this is a solenoid. So what is a solenoid? It is a copper wire taken and the length is more than the diameter. That means large number of turns are taken around a non-conducting substance. Okay. Now when you pass electricity through it, when you put the switch on, the current moves from positive to negative and you see the direction. Supposing if you are standing over here, just imagine you are seeing the direction of the current. Okay, the direction of the current, of course, we can find out with the help of magnetic compass. But just imagine if the current is in the clockwise direction. So if it is in the clockwise direction, it is what pole? It is south pole. Okay, just see how I am writing south. And if it's a anti-clockwise direction, it is the north pole. So this south I am writing in such a way that we observe that the current is moving in the clockwise direction, and this north I am writing in such a way that the current we observe that is moving in the anti-clockwise direction. So if supposing this is a solenoid and if you are standing over here and you are observing the direction of the current, and if the direction of the current is in the clockwise direction, then it's said to be south polarity, and if the current is moving in the anti-clockwise direction, it is north polarity. So this is the clock rule. In the textbook, the diagram is shown like this. See, like this. Okay, so now this is what direction? This is the clockwise direction. So clockwise direction, it is south pole. And if supposing if you change the polarity, this is the key. And if the current is moving opposite to the one that is over here, then it is north pole. North pole is anti-clockwise direction. So this is the clock rule. Now if you observe carefully while performing the experiment, we'll observe that this one also behaves like a magnet. If this is suspended in the air, it points towards the north-south direction. It attracts iron pieces. But then what is the difference between this solenoid and a permanent magnet? Now permanent magnet, you know, you cannot change the polarity. Like how I change the polarity over here, just see here, we cannot change the polarity. In which is north, that will remain north only, which is south will remain south only in a permanent magnet. But in solenoid we can change the polarity, and we can also remove the magnetism whatsoever totally. How can you remove the magnetism totally? By putting the switch off. When you put the switch on off, then this whole thing ceases to a magnet. Okay, now this thing can get converted into electromagnet if you are using a soft iron piece over here. Okay, soft iron. If you are using soft iron, then this thing turns into a solenoid, turns into an electromagnet. So what is the difference between solenoid and electromagnet? In solenoid, this we have taken is the cardboard. A copper wire is wound around a cardboard. But in case of electromagnet, instead of cardboard, what we have taken? We have taken a soft iron. Now, why do you take soft iron? Soft iron is used because it has high permeability and low retentivity. High permeability means it is able to turn itself into a very strong magnet whenever electricity is passed through it. and it is able to lose all its magnetism property whatsoever once the switch is off. That means when no current is flowing through it. Whereas permanent magnet, now they are made up of steel. Okay, why they are made up of steel? Just opposite of this, so that they can retain the magnetic property for a longer time. So we should know the difference between an electromagnet and a permanent magnet. An electromagnet is made up of soft iron. A permanent magnet is made up of steel. Electromagnet we can change the polarity. Permanent magnet we cannot change the polarity. Electromagnet we can increase the power by increasing the number of cell. If this battery has 2 cells, if we make 3 cell, 4 cell, then that much power of the electromagnet will increase. Whereas in the permanent magnet we cannot do so. So electromagnet are usually used wherever you need a very high power of magnetic field. Okay, where all it is used to pick up heavy scrap of iron. Okay, like for example, there is a scrap yard and they want to pick up heavy loads of iron, so they make use of a crane which has electromagnet in front. Of course, electromagnet has various uses. The fan which is above your head, that is also made inside. There also there is a motor which has an electromagnet in it. Then electric bell, the one that is been explained in your textbook. Of course, that is not there for your exam, so that's why I'm not doing it. But then just remember that electromagnet also works on, electric fan also works on this principle. Then it is also used to pull out iron pieces from the body of the soldiers. Like for example, those soldiers who go for war, mishaps do happen. So if the bullet or iron pieces enter their body, it can be removed with the help of electromagnet. So electromagnet has various uses and it is used in many places. Okay, it is used in the speakers also. Okay, all the speakers, if supposing you have a headphone or earphone, if you take an iron piece, it gets attracted. That shows that there is a electromagnet inside, or there is a magnet inside. Alright, so now this clock rule you all must have understood. You also understood what is the difference between solenoid and electromagnet, and how can you increase the power of this solenoid or electromagnet? By increasing the number of turns and by increasing the current. Okay, you get it between electromagnet and permanent magnet. We studied about the dissimilarities between electromagnet and permanent magnet. Now what is the similarity? Both of this solenoid and the permanent magnet, they point towards the north-south direction. Alright, and they both attract iron pieces. So that is a similarity between both of this. Okay, now we are going to study about the Lorenz force. Now Lorenz, this scientist, what he did was, he took a solenoid. Now you know how to draw a solenoid. I'll draw it one for you. So something like this. This is a solenoid in short, and a battery, okay, a key, a rheostat to change that amount of current is been taken, and the electricity is passed through it. This is a solenoid in short I have drawn, okay, and the current is moving like this. Now Lorenz, what he did was, he took a horseshoe magnet and he kept it over here like that. He didn't kept it, but he held it over there. So this is the north and south. So when the electricity is flowing through this, and when the magnet is brought next to this solenoid, there is a force acting on this. Okay, this force is observed to be moving in the upward direction. Now see the magnet, the polarity of north is down and south is above, and the current is moving from positive to negative. So then the force is being observed. Now that force is given by the formula IBL. I call it BIL. Okay, it's easy to learn BIL. So the force depends on three parts. One is current, one is magnetic field, one is the length of the wire. Okay, so F is equal to IBL. Okay, and the unit of that force is Tesla or Weber per meter square. You must have heard about Tesla cars. They are the battery powered cars in America. Okay, so now that Tesla has been used, that word company name Tesla has been taken from here. So whenever a solenoid is taken, electricity is passed through it, and when you take a horseshoe magnet and when you bring it next to it, there is a force acting which will be upward direction. Now what happens if you change the polarity? Now this north is brought here and south over here, then this magnetic field will be the force acting on this will be in the downward direction. It will change. So just remember, it depends upon the Fleming's left hand rule. You know what is Fleming's left hand rule? Hold the left hand in such a way they are perpendicular to each other. See the thumb, the forefinger and the middle finger, they are all three in a perpendicular direction. Did you observe? See, they are in perpendicular direction. So if the current is moving in the like this direction from here to here, and the magnetic field is around like this surrounding magnetic field, then there is a force acting in the upward direction. Okay, so that is Fleming's left hand rule. Okay, so did you understand the Fleming's left hand rule? Fleming's left hand rule is, imagine you hold your left hand in such a way that the thumb, the forefinger and the middle finger are perpendicular to each other. The current is denoted by the middle finger, the magnetic field, the forefinger, and the force is the thumb. Okay, I imagine this to be FBI. I am the FBI. So I am holding a gun like this. So if I am the FBI, F is the force, B is the magnetic field, I is the current. So you can learn it that way. So whenever the current is moving this way, magnetic field is perpendicular to it and the force acts on it. Okay, they always have to be perpendicular to each other. This all things is used in DC motor. They have given a lot of explanation of DC motor in your textbook. Please refer it, since it's not coming for your exam. That's why I'm not teaching that to you. Now we study about the Faraday's experiment. Now there was a scientist by the name of Faraday. Now he said that just as whenever electricity flows through a wire, there is a magnetic field around it. So magnet should be able to produce electricity also. So this was a very important decision or thinking that he had. Because of this we have a Tesla car. Okay, that is because of the magnetic effect of electric current. Okay, so what was his experiment? He took a galvanometer. And now what is a galvanometer? A galvanometer is used to detect the current, and he connected to the solenoid, and he moved a magnet, a very powerful magnet, next to it. Then he observed that there is some deflection in the galvanometer. Okay, so let's study the experiment. So this is, okay, so here you have a solenoid and there is a galvanometer over here. Galvanometer is used to detect the current, and when you bring a magnet next to it, now if you get the magnet next to it, there is no movement, then there is nothing observed over here. But if supposing if you move this magnet north pole very fast towards this solenoid, then what will happen? This will have a polarity of north pole and this will have a polarity of south pole, and this needle will point towards the north direction. Again I repeat, when you bring a magnet next to this solenoid, nothing will happen. But if you bring it very fast, okay, when this magnet is brought very fast next to the solenoid, then you will observe the same polarity over here. If north is brought next to this, then this will have, the solenoid will have north polarity, and of course the other one will have south polarity. This needle will point towards the north. Always remember, the needle points towards the north. Now if you keep it stationary after you bring it, then what happens? then this galvanometer comes back to its place. This one polarity is gone. It ceases to be a magnet. It is just a solenoid now. Okay, it loses all its magnetic property. Now what happens if you move this magnet very fast on the other side? Then in that case what happens, this will have south polarity, this will have north polarity, and the needle, of course, it will point towards the north direction. So now the magnet, when it is moved very fast, then only you can see that this solenoid turns into it produces electricity in it. So electricity produced is such that it tries to oppose the movement. This is opposition, na. So the current produced in this is such that it tries to oppose, like for example, north and north repel, and south they repel. So when you bring the north polarity near this magnet, this will turn into north. That is repulsive force. So there is a repulsive force which is produced, and it lasts so long as you move this magnet. Now moving of this magnet is also called as magnetic flux. Now what is magnetic flux? Now if you see this magnet, it has a magnetic field around it. Okay, you may not have seen it, but it does have a magnetic field around it. Now supposing if you get an iron piece over here, it may not get attracted that strongly, but if you get it over here very nearby to the magnet, then there will be a larger force attracting it. That means here the magnet has a varying magnetic field, from a very strong magnetic field to the less strong magnetic field. So that varying magnetic field, whenever you move this magnet very fast, it has a varying magnetic field. That is called as magnetic flux. So what is magnetic flux? Magnetic flux is a varying magnetic field. Now so long as there is a magnetic flux over here, there is electricity produced in this. Now the electricity produced in this depends on the number of turns or the area of cross section of this coil, or the strength of this magnet, or the magnetic flux linked with it. When you move this magnet very fast, then the electricity produced will be a very stronger, or maybe if you take this magnet a stronger magnet, then you can see that the current produced is more. Okay, so that is what Faraday found out. What did Faraday found out? So the electricity produced in this, when there is a magnetic flux in this, and the current in this opposes the movement. That is Lenz's law. Lenz's law says that the current produced in this is such that it tries to oppose the movement. Alright, did you get it? So now where is this used for? This is used in AC generator. Whenever you get the electricity, you studied in this household electricity, the electricity is produced near the dams, and from there it is coming towards the city. So how it is produced, it is there in that part which I have explained to you. Okay, just refer that household electricity, you know how the electricity is produced, and that is AC generator. Okay, the below the waterfall, those turbines are kept, those are AC generator. They are converting mechanical to electrical, and sometimes back we studied about DC motor. So DC motor is electrical to mechanical energy conversion. You will be asked in your exam AC current and DC current, difference between AC current and direct current. Like AC current, it is alternate current. The frequency changes 100 times per second, 50 times plus, 50 times minus. But DC motor is current in one direction. Okay, and in DC motor the magnitude is constant, and in AC generator the magnitude is varying. Okay, now AC generator we get it from mains or from AC generator, and DC motor we get it from battery, the inverter which you have, that gives you DC current. So just see, if you go on the description box, there is a link given. So there are all the important definitions and all the important formulas and proper things which all are coming for your exam is being given. Okay, so please go through that and learn that nicely. So students, now we'll be studying some of the important topics in this. Not that this is not given in my notes. You can get this in my notes. You can learn it from there. Please excuse my handwriting. So what is electromagnetic induction? Electromagnetic induction, as I have told you, whenever there is a varying magnetic flux, there is a electricity generated. So the definition, It is a phenomenon in which an EMF is induced in the coil if there is a change in magnetic flux linked with the coil. Now Faraday's law. Faraday he brought in two laws based on the induced EMF. Whenever there is a change in magnetic flux, then EMF is induced. Now you observe that when you get a magnet, okay, permanent magnet next to a solenoid, there is an EMF being generated in the solenoid. Okay, now if you bring the north pole near to solenoid very fast, okay, there is a strong magnetic flux, then the solenoid, the end near to that magnet, will turn its polarity to north and north. And if you take that north pole magnet away from the solenoid, then the polarity of the solenoid changes from north to south. And if you bring the south pole of the magnet next to the solenoid, what is the polarity at the end near the magnet will be? Of course, south. Okay, so it is such that tries to oppose the movement. So Faraday's laws are based on that. Whenever there is a change in magnetic flux, then EMF is induced. The magnitude of EMF induced is directly proportional to the magnetic flux. The induced current depends on the rate of change of magnetic flux and the number of turns of a coil. Now the induced EMF is given by Fleming's right-hand rule and Lenz law. Now we studied about current carrying coil in a wire. Okay, when it has a magnetic field, that is given the force acting on it when a magnet is brought next to it. That force is given by Fleming's left-hand rule. Over here, the induced current, the rule is been explained with the help of Fleming's right-hand rule. So everything the same, FBI, but only here in this case you have to make use of the right hand. Okay, FBI, force, magnetic field, and the current. Okay, you don't have the application of this. Neither are they going to ask you Fleming's right-hand rule, but just see it's just opposite to Fleming's left-hand rule. Okay, now Lenz law. The direction of the induced EMF is such that it opposes the cause which produces it. Now it is used in AC generator and transformer. Now what is DC current and AC current? Okay, DC current is that inverter current. You have inverter at home. Okay, so that is DC current. It is a current of constant magnitude. It flows in one direction. It is obtained from a cell or a battery. AC current, it is a current of varying magnitude. It reverses its direction periodically. It is obtained from AC generator and main. Now we study about the advantages of AC over DC current. We make use of AC current. We don't make use of DC current at home. DC current is only for short time. Whenever AC current is not there, we make use of inverter. So what are the advantages of AC current over DC current? AC current is cheaper. For getting inverter, you have to spend a lot of money. And of course, for maintenance also you need a lot of money for generator at home. Okay. So AC current is much cheaper comparatively. It is greater, it has a greater efficiency. Okay. It has a greater efficiency. I'll correct this. It has a greater efficiency. It is easy to convert it from one form to another. You know, electrical energy gets converted into sound energy, then chemical energy, then heat energy. So AC current can be transferred from one form to another. Whereas DC current, we cannot use geyser with it or fridge with it, or maybe higher source appliances with that. Maybe the battery will get over fast or it can get damaged also. So that's why it's easy to convert AC to other forms rather than DC source. Its magnitude can be increased or decreased easily. You have step up transformer, step down transformer, in which the current can be increased or decreased, which is connected only to AC generator. In DC we cannot do that. It can be transmitted easily over long distances without much loss of energy. So whenever electricity is transferred from the outskirts to the city, it is usually AC current, and you make use of step up transformer, and sometimes some places when the current is to be brought down, that time step down transformer, the voltage has been brought down there. Okay, so that is the advantages of AC over DC current. These are there in my notes. You have better printed notes, please go through it. Okay, then distinguish between AC and DC motor. Now these things is cancelled from the board exam, for the board exam, but it's very useful for you to know, okay, for higher studies in 11th and 12th. So please go through it, it will be helpful for you later. So AC, what is the energy conversion? Mechanical to electrical. DC, electrical to mechanical. AC works on a principle of electromagnetic induction. We studied about electromagnetic induction shortly. Works on a principle of force acting on a current carrying conductor placed in a magnetic field. Now, AC current makes use of two coaxial slip rings. Inside a AC generator, there are slip rings. If you see the explanation, of course, that's not coming, but if you see the explanation of AC generator, there are two slip rings present. And in DC motor, it makes use of two split rings. So these are the 3 points. Please go through it. Now, similarities between AC and DC motor. Both rotate in the magnetic field. There is a magnet and there is a coil in between, and the coil moves in the magnetic field. Both has transformation of energy in one form to another. In case of AC, it is mechanical to electrical, and in case of DC, it is electrical to mechanical. So that's all we have for this lesson. If you have liked this lesson, if you have understood, and please do not forget to like, share and subscribe this video so that you will get more videos of this. Till then, bye bye, see you.